Hi, this animation will show how time dilation in special relativity is symmetrical. In my first animation we saw that simultaneity is relative. Events that occur simultaneous for me don't look simultaneous for anyone moving relative to me. And events that are simultaneous for someone moving relative to me don't look simultaneous to me. In my second animation, we saw that time runs slower when moving by a factor of the square root of 1 minus speed squared divided by light speed squared. Now let's consider two observers O and O accent with reference frames xt and x accent t accent respectively. With the x and the x accent axis aligned. And now suppose that observer O accent moves with a constant speed v in the x direction. And when observer O accent passes observer O, both time t for O and time t accent for O accent are both 0. In that case, the relationship between times t and t accent is given by the following formula. T accent equals t minus speed times distance x divided by light speed squared divided by the square root of 1 minus v squared divided by light speed squared. It reflects the relativity of simultaneity and the slowing down of moving clocks, as we shall see. Assume that the speed is 0.8 times the light speed, and in both reference frames we put clocks which are 0.8 light seconds apart, as measured by observer O. Then at time 0, the clocks in O and O accents reference frames give the following times. These are the clocks of observer O accent at time t0 and spaced 0.8 light seconds apart. So these are their x coordinates. And these are the clocks of O. The time t is now 0. As you can see, the relativity of simultaneity is obvious. The clocks from observer O accent are not synchronized according to observer O. To see if the clock from observer O accent runs slower, we must follow it and compare it with the clock in the frame of observer O at the same distance, the same x. At t0 it reads 0, just like the clock at the same x from observer O. Let's move on 1 second as counted by observer O. The clock from O accent reads 0.6 seconds against 1 at the corresponding clock in the frame of observer O. So according to observer O, the clock at O accent runs slower. Let's go on for another second. The clock from O accent reads 1.2 seconds against 2 seconds at the corresponding clock in the frame of observer O. So the clock from O accent is running at the rate of 60% of the clocks from O. Now, is the clock from O also running slower than the ones from O accent? According to the relativity principle, it should, and it does. To see this, we must now follow the clock at observer O. It reads 0 to start with, just like the clock at the same x at observer O accent. And let's now compare them after 1 second. The clock in the frame of observer O accent reads 1.67 seconds and only 1 second at observer O. So, according to O accent, the clock of O runs slower. Let's move on to the following second. The clock in the frame of O accent reads 3.33 seconds and only 2 seconds at O. So, the clock from O runs at a rate of 60% of those from O accent. Both are right in claiming that the other one's clock is running slower. It is running slower at a rate of only 60% in the case that the speed is 0.8 times the light speed. And in fact, the square root of 1 minus speed squared divided by light speed squared is 60% if the speed is 0.8 times the light speed. This is how time dilation is really symmetrical. But what if observer O accent first moves to the right and then returns to the origin? Let's start from the beginning again. Let's move on 1 second as counted by observer O. And 1 more second. And now let O accent return towards the origin. Upon returning, the speed will change from 0.8 times light speed to minus 0.8 times light speed. And also the term involving x in this formula changes sign. And so the times, the clocks at O accent corresponding to the synchronized ones at O will change like this. Now we move on 1 second and 1 more to bring observer O accent back to the origin. And we see now that the clock at observer O accent is running behind the one from O. Less time has passed for observer O accent during his trip than for O. The symmetry between both got lost because O accent made a return and O did not. This will all become more clear when I illustrate it geometrically, but that is something for a later animation. In my next animation I will illustrate the Lorentz contraction. Perhaps I will see you there, and thanks for watching.